Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on polar equations. Now, this is going to be our last lesson in our chapter for applications of trigonometry, the 7th lesson of them all. And what I'm going to do is I'm going to work through the exact same notes that I worked with my own students inside of the classroom. Now, for polar equations, I kind of keep things fairly simple, but what we're going to do in this lesson is we're going to talk about what are polar points or polar coordinates, how to plot them, as well as how to determine the different representations. And then we're also going to focus on the converting between the polar and rectangular coordinates as well as equations. We're not going to get into the graphing of polar coordinates in this lesson. So we're just going to kind of focus on those three main topics, because I know obviously we could get a lot more advanced with the polar equations, but we're just going to keep it simple for this lesson. So the first thing I did to kind of start off the lesson is I gave students 2 points and I said, all right, why don't you guys plot these points? And, just plot them. I put them in quotation because I didn't want students to try to be exact. I just wanted them to pretty much say, where are these points on a coordinate grid? And most students, didn't take them long. They kind of plotted the points. And then what I wanted to do was talk to them like, well, how did you arrive at those points? For instance, on these points here, did you evaluate the square root of 3 divided by 2 to be 0.86 and 1/2 to be 0.5 and then plot it that way? And most students said, no, I didn't do that. I basically recognized this was on the unit circle, so therefore I kind of plotted the point. And I think, that's very, very interesting here what you did. Rather than thinking of what the x coordinate is and what the y coordinate is, what you thought about was what is the distance away from the origin, which in this case is 1, and the angle, which was 30 degrees, right? And then this next case, again, did I say, did you take out your calculator and evaluate for the square root of 2? And no, a lot of them estimated, which is good because that's one thing I taught them in class, that the square root of 2 is roughly somewhere going between 1 and 2. Hopefully we recognize that the x coordinate is negative, so that's why it's going to be in the second quadrant. The x coordinate is negative and the y value is positive, so it's in the second quadrant. But again, if we look at this, we can recognize, we can actually label this point as, yes, we have the x coordinates, and yes, the y coordinates. But we can also say, what is the angle here? Now, again, if we recognize the two legs of a triangle are exactly the same, we know it's going to come from a 45, 45, 90 triangle, right? Like when you have coordinates, when you have legs that are the same, then this was going to be x square root of 2. Now, the students also could use the Pythagorean theorem to figure out the magnitude, which ends up would equal to 2. But again, you can see that the distance, the hypotenuse using the Pythagorean theorem, kind of speaking a little bit ahead. But you can see here that distance is going to be 2. And if that's 45 degrees, this angle here, even though that's 45 degrees, we could say this angle would be 135 degrees, right? Because from here to here, from there to there is 135 degrees, right? But inside of there would just be 45 degrees. So what I'm doing is, rather than representing these points as x and y coordinates, I'm representing the points as how far are they away from the center of the coordinate grid, the origin, and then what are their angle, right? And you can do this for both these examples. You could say this is going to be 135 degrees, all right? And I think by looking at it this way, you can see it's a little bit easier to kind of understand where these points are, like they have a distance and then the angle. Well, to represent both these ways is what we call our polar coordinates. And our polar coordinate system is basically a way for us to, it's kind of the same thing on our x and y axis. All right. And we're going to call the origin what's going to be the pole. And a ray from there is going to be our polar axis. So every point can be written as r comma theta, where r is going to represent that directed distance away from the pole. And theta is going to represent the angle, or the directed angle. Now, again, we're going to be using this in standard form. So one of the things I just kind of it's not really the radius, but a lot of times I will use the radius to kind of make sense or make some connections for students. So we can think about this smaller circle here. We can say the radius is 1. So that's like the unit circle. So it's really just like expanding different, circles of a different radius. But again, I don't want you to be confused in thinking them as a radius, because they're not. They're a directed distance. And when I talk about directed distance, the reason why I underline them is because direction matters. You can go in a positive or a negative direction, and that doesn't make sense if you're thinking about them as a radius. So what we'll do is when we get into some more of these points, we'll start to see why that is the case. All right, but the first thing I want to do is just have students practice plotting coordinate points. And again, remember, this is not an XY graph, but what we're going to do is we're going to focus on now dealing with the directed distance and the angle. So the first thing I tell students to kind of do is find the angle in standard form, right? So the angle of 150 degrees, we can say that we can assume these are going by 30-degree increments. So 150 degrees would be over here. And then we have a directed distance of 3. So it's kind of like counting 3 rings here. 1, 2, 3, out. And we can do the same thing for B here. Now that's going to be negative pi over 3. So that's going to be down this way. And again, you can think about this in terms of thirds, right? So, 1/3, 2/3, 3/3, right? Just break it up into thirds. And then that's going to be a distance of 5. So 1, 2, 3, 4, 5 along that polar axis. And therefore now you can see that is where your coordinate point is, okay? And that's basically plotting the points. And then I gave the students some examples and I said, all right, let's just go and practice them. A lot of students, really didn't have issues with this, except when we got to the radians, they kind of forgot how to work through that. But let's just go and plot these. I'll label these as A, B, and C. So the first one's going to be 30 degrees, and we'll do 3, 1, 2, 3. I'll label this as A. For B, that's going to be at 90 degrees, 1. So again, I go into 90 degrees, and then I'm going a distance of 1. For C, we're going to do 135. Now, again, that's going to be between 30 and 60, and it's going to be a distance of 5. So 1, 2, 3, 4, 5. Then we have D, which is 2, negative 120. So negative 120, again, we need to think about that. That's going to be 60 degrees away from the x-axis. Again, we're going in the negative direction, right? So remember, in standard form, we have the positive direction and the negative direction. So we're going in negative direction. And again, if these are 30 degree increments, then 60 would be down here, and that's going to be at A2. So we'll do, that's going to be D. And then negative 7 pi over 4 is an interesting one, because again, you got to remember, you're going in the negative direction again, right? So remember, all halfway around a circle is pi, just in the negative direction. Well, in terms of force, that's going to be 4 pi over 4. All the way around the circle is 2 pi. In terms of force, that would be 8 pi over 4. So if I'm going in the negative direction, this is going to be negative 4 pi over 4. This would be negative 8 pi over 4. But I only need to travel to negative 7 pi over 4, right? So you could do negative 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. So you can see it's going to be, the polar axis is going to be right here. And therefore, then it's going to be at 2. So 1, 2. So that's going to be my E. And then for F, same kind of idea here. We're at 11 pi over 6. So now that's going to be in the positive direction. Well, again, halfway around a circle is pi. In terms of 6, that's 6 pi over 6. All the way around the circle is 2 pi. In terms of 6, that's going to be 12 pi over 6. So again, I'm not going 2 pi, 12 pi over 6. I'm only going to go a pi over 6 short. Which again, if you can see, actually, this circle is broken up into 6 parts. So 1, 2, 3, 4, 5, 6, right? 7, 8, 9. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 11 pi over 6 is going to be all the way to here. And then again, we're going out to 4. So 1, 2, 3, 4. And there you go. So that's how you basically plot these points. From there. And again, you want to typically find the angle first, radians or degrees, and then go ahead and plot with the directed distance. Now, the one thing that kind of brings up then is, are these again the same thing as the coordinate points? And that's what I wanted to bring up over here. Like, you can see this coordinate point didn't change. Like, I could write this in this rectangle form or the polar form, but you can see how they create the exact same coordinate points. So if I give you a coordinate point, in terms of like x, y, I can represent that as a polar point as well. So there are some equations, and a lot of people get confused. They're like, I'm not going to remember these, like how, because I don't give them to them on the test. So, what should we do? How can we remember these? So what I went over with my students, I said, this is all the same information you already know. Let's say we have a random XY point on a coordinate grid. All right. We know that that point has a distance. Actually, let me do it this way. Let's use blue. So we know that point is going to have a distance away from the origin, which is r. Okay? And we also know that that xy point is really representing a x distance and a y distance away, right? So this coordinate point is an x and a y distance, which creates a right triangle. So therefore, that's how we get the x squared plus the y squared equals r squared. The other thing is, since we have a triangle, we could say that that is going to represent theta, right? So if we have this right triangle, that represents theta. Well, then again, the tangent of theta is equal to y over x. So you can see just by like sketching the graph, and again, that's what I did with the students at the beginning of class. I just said, let's just plot the point. Forget about everything else. Plot the point. And just from plotting the point, what we already learned is, or what we already knew, is the Pythagorean identity and the trigonometric function. We could create those. Now, and that was what we did at kind of like at the beginning of our unit on trigonometry. Then we started getting into, trying to get prepared for the unit circle. And when we got prepared for the unit circle, what we did is we said, all right, let r equal 1. Now, when r equals 1, so typically we have sine of theta is equal to y over 1. Well, we didn't really need to write, well, remember, actually, hold on. Sine of theta is y over r, right? And most students were like familiar with sine of theta is opposite over a hypotenuse, right? Cosine is adjacent over hypotenuse. So then we said cosine of theta is x over r, right? Now, again, we simplified this a little bit in the point that we said, well, when r is equal to 1, so when we said when r is equal to 1, then we could just say sine of theta is equal to y and cosine of theta is equal to x, right? And therefore we had, this was cosine of theta, and this represented the sine of theta. And that was important because that's what we refer to as the unit circle, cosine of theta, sine of theta. But now we're going back to, well, if you look back at your polar coordinates, r is not always 1, right? R can be these multiple different, these different values, these different distances. So how is that going to impact our points? So again, like let's pretend r was 2 in this case. Like let's pretend r is out here. So what would that give us in terms of our x coordinates, right? So if r is equal to 2 out here, well, all that's going to do is you're just going to multiply 2 times cosine of theta to sine of theta. Okay, so you can think of that r as like a scalar. It's multiplying by the horizontal as well as this vertical component of the points, right? Because it's double the horizontal distance and double the vertical distance. So in reality, all we're going to do is whatever, we know that x is cosine, y is sine, right? But that was when r is 1. So when r is any number, we're just going to multiply it by our sine and our theta and our cosine. And again, you can see in our original problem why this kind of makes sense. We can see that when you multiply by r on both sides, you get r times sine of theta equals y. And if you go back to cosine of theta is x over r, you multiply by r on both sides, you get r cosine of theta is equal to x. So hopefully you can see, how we got these green equations as well as how we got the blue equations just by sketching the graph and using what we already know from trigonometry. Now, that was typically the easy part of the beginning of the lesson. Then we get into the multiple representations, and this is where students usually get pretty confused because they have a hard time visualizing these multiple representations. So one of the common questions that comes up is determine 3 representations of a following point. And typically there's going to be a restriction because again, when you recognize when we have angles, we could always use coterminal angles, right? We could always add and subtract 360. We can always add and subtract 2n. That's always going to produce infinite many angles. So typically there's going to be a restriction of what the angles can be. And in this case, the angles have to be between negative 360 and positive 360. So what I'm going to do is I'm going to try to do my best here. And actually, I'm going to go back to using green to kind of represent this. So the first one is, let's say we have 4 180, right? And that makes sense, right? We have 180 degrees. Okay, so there's our angle, 180. And then we have 4, 1, 2, 3, 4, directed distance, done. Now, we can't add 360. Well, we can, but if you add 360, then that's going to give you, let me do this. So that'd give you 180 degrees plus 360, right? Because typically if you want to find coterminal angles, you just add and subtract 360. But the problem is we get 540 degrees and that does not satisfy the restriction, right? So that's why we're not going to include that answer because it doesn't satisfy the restriction. Okay. So therefore we look to, well, what about subtracting 360? Well, if I subtract 360, that's going to give me negative 180, right? And that works. And you can see that produces the exact same angle. If I did negative 180 and then go over 4, you can see how that produces that point. Now I can't subtract 180 again because that would give me negative 540, which again would not satisfy the restriction. So what else can I do? So here's where I actually want to go back and utilize like the idea of vectors just to kind of make a point. So when we are dealing with vectors, one of the things we talked about with vectors was the scalar. So if I had here's vector v, and vector v has an x and a y component, right? Well, if I looked at negative v, right, just that same vector multiplied by negative, all that's doing is that's reflecting it about the origin to give me, let's actually call this, let me call this t. So that's going to give me negative x comma negative y. Now, t is equal to the opposite to v, right? Or the negative v. And what's important about that then, negative t is equal to v, right? So here's vector v, here's vector t. If vector v represents xy and vector t represents negative x, negative y, well, you can see that this is just the negative scalar. T is just the negative scalar of v. And if you did the opposite then of t, that would take you back to your original vector. So what I'm trying to propose to you, or I'm trying to understand is these vectors, if you're trying to think about that scalar, when you multiply by a scalar, what you're doing is you're reflecting it about the origin. So when you have that scalar, you're multiplying by the x and the y components. And what that does is and when it's negative, that is going to reflection about the origin. So if we kind of go back to our understanding here, what is this r doing? Well, you're multiplying the r not by just the cosine, not just by the sine, but by the x and the y. So therefore, you can think of this r as also like a scalar. It's going to have that same kind of impact on your polar points like it would a vector. Now, again, these are not vectors. That's why I did this in blue, because I don't want you to get confused. But my point that I'm trying to make here is that if you were to take the following vector, 0 degrees, 1, 2, 3, 4, right? If I was going to do 4 comma 0 degrees, that's going to take you over here. But again, my point is those are not the same vectors, right? Obviously. But if I make this a negative, what that's going to do is that's going to reflect it about the origin. So it's over here. So actually that point, negative 4 0 degrees, is this point being reflected about the origin, which is going to produce that point. So therefore, those two angles work. And again, you could do 0 degrees or you could do 360 because it could be equal to 0 or it could also be equal to 360. Now, so people have a really, really difficult time understanding this. Actually, I don't want to make this negative. There you go. So then I'll do this is a negative 4 comma 0 degrees. So people have a hard time, seeing this or visualizing this. So a lot of times I said, well, we can always go back to these equations, right? Don't forget x equals r times cosine of theta, right? So maybe let's go ahead and check our work. So x equals 4 times the cosine of 180 degrees. And therefore x also has to equal negative 4 cosine of 0 degrees. Okay, so let's go and play around with this. Cosine of 180 degrees, right, based on this unit circle here, is going to be negative 1. So I have 4 times negative 1, which equals x equals negative 4. Got it. I'm familiar with that. I agree. That's fine. So if I do x equals negative 4 0 degrees, I'm going to have a negative 4 times cosine of 0, which is over here, right, which is 1 comma 0. So therefore, that's going to give me x equals negative 4. And the same thing is going to work because, again, when you're multiplying this negative 4, because that's the r, you're multiplying that by cosine of theta and by sine. The cosine and the sine are both going to be positive, but when you multiply by a negative 4, you can see why that's reflecting about the origin. So it's a confusing section, or it's just a confusing point to make, the one thing I kind of tell students to do is, one, always add and subtract 360 or 2 pi. That always will give you a different representation. Make sure you find the restriction. And then the second thing I want students to look at is understand that when you're multiplying by the negative, that is reflecting about the origin. Okay. So it is something though that we want to practice. And that's why I kind of gave the students, a little bit more time to kind of practice and say, all right, let's go and find some different representations. So the first one is I have a negative angle. So therefore I know that the only thing I can really do here to find an easier one is I can take negative 4 halves. I'm going to add 2 pi, which would be 8 pi over 4. So that's the easiest thing I can do. And that's going to give me 7 pi over 4. Okay, so let's go and plot the graph. Actually, I should probably have done that first. First thing you want to do is plot the point. So I have negative pi over 4, so that's going to be somewhere here, and then 5. So 1, 2, 3, 4, 5. Okay, so there's my point here, right? And again, this is not a line, this polar axis, but I want to kind of see this here. So again, that is going to be negative pi over 4, right? But here's the point. Okay. Now again, all I did was I added 2 pi to get this angle. Now again, I can't subtract 2 pi because that would be larger than our restriction. And again, our restriction is between negative 2 pi and 2 pi, or negative 360 and positive 360. I'm using the same restrictions as my other problem. So I can only add. But now there's really nothing else I can do except for finding the reflection. So again, I got to understand, all right, well, what is that reflection point, right? So remember, the reflection is going to be, the negative is going to be, when I deal with negative 5, that is going to be a reflection about the origin, right? So basically it's going to be this exact same point, 1, 2, 3, 4, 5, right here. So that's going to give me the negative 5 radius. And now what I need to do is understand, well, what is that angle here, right? So I could do this angle 2 different ways. I could do this angle, or I could do that angle. But again, my point is I want to take that angle to get me to here, which again would be like, you can think about it as positive 5, but once I make that a negative, it's going to reflect it back over to here. So again, what is this angle? Well, if this is pi over 4, negative pi over 4, that means this angle right here is going to be a pi over 4. So I'm going to be pi over 4 short to pi, which would be 3 pi over 4. And if you did the negative version, you could do I could do pi over 4 over pi, which would be a negative 5 pi over 4. So that would be negative 5 pi over 4. This one would be 3 pi over 4. And again, you can think of the 5 going this way, and then the reflection making it negative takes you out that way. All right, so now let's do a negative angle. Now again, graphing the negative angles gets confusing. So what I like to do is I like to say, forget about the negative angle. Just graph 120 degrees. So we're going to go 120 degrees. That's going to be 60 degrees away from the x-axis. And then I'm going to go to 3. 1, 2, 3. Okay, so that is my 120 degrees. But now what I'm going to do is I'm going to say, all right. Oh, and let's go and find a different, whatever. Now let's go and figure out the negative 120 degrees. Well, negative 120 degrees is going to be basically this point reflected about the origin. So 1, 2, 3. And you can see that here, this polar axis is on the same line here, right? So that's going to be my negative 120 degrees. All right. So negative 120. So what I like to do is graph the angle first with the positive and then flip it over. All right. Now I do want to think about, so here is negative 120. What is another way that I could represent that? Well, if this is going to be a negative 120, I could also do the negative version of that, right? So I could do negative 3 and say, how far is that going to be from 180, or just subtract? And that'd be negative 240 degrees, right? So if you did negative 240 and then negative 3, that would take you over to here. Or we could think about just doing the positive angle, right? So let's kind of do our calculations. From here to here is 120 degrees. That means from here to here is going to be 60 degrees. And again, using your math here, that means that is going to be 60 degrees as well. So I could use the positive 3, and I could also say positive 3, negative 60 degrees, Or I could use positive 3, positive 300 degrees. Okay, because again, if that's positive 3, I could do negative 60 degrees, or I could do positive 3, 300 degrees. And again, it's a confusing thing. I think it's one of those points that, you just need to kind of work through a couple different examples to really kind of refine your understanding of plotting these points and especially dealing with the negative. But the best thing I can just recall with you is, again, one, you can always check your work by using x, r cosine of theta, r sine of theta. But then also really just kind of think about them as their reflection. So when you see that negative, just remember that is representing a reflection about the origin. So it's not, this is positive 3, 120, right? That red dot is positive 3, 120. So when I make it negative, I'm reflecting it about the origin. So I like to do the positive version first and then apply the reflection after that. All right, so again, kind of like to check our points here, like we did in this last example, we can always convert them between each other. So the conversion between polar to rectangular is simply just r times cosine of theta, r times sine of theta. Now, I caution my students not to use a calculator in this case, because typically for free response, we're not going to be dealing with decimals. I'm going to ask for the exact answer. And then when you're dealing with a multiple choice problem, your answers are not going to be typically in decimals anyway. So you're going to have to find this exact answer. And again, you should be able to evaluate these hopefully without using a calculator anyways, because we have the unit circle. Now, the nice thing about this though, too, is we can also verify what our answer is going to be. So in this case, we have the polar coordinate 4, 300 degrees. If I was to go ahead and plot this, all right, I have 300 degrees is going to be down in the fourth quadrant, and we're going to have a distance of 4, right? Sorry. What was I trying to do? I don't know. Well, 300 degrees. 300 degrees is going to be a point on the unit circle, which is 1/2 common negative square root of 3 over 2. But again, so I know that angle is producing something in the fourth quadrant. It doesn't matter if it's a distance of 1 or a different distance of 4 along this polar axis here. It's still going to be in the fourth quadrant. Now, as I convert them, 4 times 1/2 is 2, and then 4 times negative square root of 3 over 2, you can see that I have a positive x and a negative y, which again produces a rectangular point that we know would be in the fourth quadrant as well, right? So that's a good way to kind of check your work, understanding the theta to make sure you're in the right quadrant, and then as well as comparing that to your x and the y coordinates for your rectangular equation. So those are the problem I did with for my students. Now let's just go ahead and practice again, just another example. So again, here I'm going to have x equals 2 cosine of 225 degrees, and y is going to equal 2 times the sine of 225 degrees. Okay, so again, it's going to be helpful to kind of know where 225 degrees is. Well, again, that's going to be in the third quadrant. And again, hopefully you know that coordinate point is negative square root of 2 over 2, common negative square root of 2 over 2. Okay, so I have 2 times negative square root of 2 over 2. And the y is going to equal 2 times negative square root of 2 over 2. And therefore, the 2's will divide out, and you'll get x equals negative square root of 2, and a y equals negative square root of 2. So therefore, we have negative square root of 2 times, or comma, negative square root of 2. All right, for the next example, you could be, oh, it's a negative. I hate negatives. I'm confused. But again, you don't really need to worry about that, right? Because all we're going to do is follow the formulas. X equals negative 3 times the cosine of 5 pi over 6. And y equals negative 3 times the sine of 5 pi over 6. Now, I'll put these in parentheses. You could know that 5 pi over 6 is hopefully in the second quadrant, right? So therefore, the coordinate point here on the unit circle would be negative square root of 3 over 2, comma, 1/2, right? X is negative, y is positive. However, hopefully you recognize that since this is a negative 3, my true point is actually going to be in the fourth quadrant, right? Because it's going to be a reflection about the origin. So my answer should be a positive x and a negative y. So as long as I do this correctly, I should have a point that's actually in the fourth quadrant, not the second quadrant. So let's go ahead and work it out. So I have a negative 3 times the cosine of 5 pi over 6, which is a negative square root of 3 over 2. And therefore, that will leave me with a positive 3 square root of 3 over 2. And then over here, I'm going to be left with a 5 over 6. So that'd be a negative 3 times 1/2, which is going to equal to a negative 3/2. So again, my x is positive, my y is negative. You can see how that is going to produce something in the fourth quadrant. And then my polar point, it's not going to look very nice, but I'll just leave it in its exact form, and we're good to go. Now the next one is going from the rectangular to polar. And again, a lot of students they're like, I don't remember the formulas and blah, 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 blah. But the way that I think about this is just go back to our warm-up. Like if you have a coordinate point, right, an xy, then just plot the xy. Like you don't need to memorize anything. Plot the xy. You know that the distance xy to there from the origin is going to be r, which is technically the hypotenuse of a right triangle that you can create, right? Because negative 2 represents the horizontal distance away from the origin, and negative 2 square root of 3 represents the vertical distance. And even though negative 2 square root of 3 might not be a nice number, as far as one that you can visualize how long it is, what you can do is, you can still use the Pythagorean theorem here. So all I did was I just plugged them in. This squared plus this squared equals r squared, or that distance. And again, not whipping out my calculator and getting to calculations, I get negative 2 squared is 4. Negative 2 times square root of 3 times negative 2 square root of 3 is going to give me 12 r squared. And this gives me 16 equals r squared, and r is going to equal 4. So that is going to be my r equals 4. Now, the next thing is where it gets a little confusing is figuring out my angle. So I'm not sure why I didn't show my work. Oh, I did my work over here. I was like, where did I do my work? So the next thing is understanding, all right, there's my angle theta. I need to be able to figure out theta too. So I go ahead and find tangent of theta. That's negative 2 square root of 3 divided by negative 2. Therefore, I do tangent inverse of square root of 3. Hopefully by the unit circle, you recognize that's going to be this point over here, which is going to be 1/2 comma square root of 3 over 2. So when I take the y over the x, I get a square root of 3, which is 60 degrees. Now again, you could obviously use your calculator. Just make sure it's in degree mode. That's plus 180. But the thing is, I get 60 degrees. This coordinate point is not 60 degrees, right? This is 60 degrees. So if I want to get the point from here to here, what do I do? And so what you need to understand is, well, from here to here is 180, and then you add 60 degrees, right? Because again, we're trying to find the angle in standard form from here to here. So 60 degrees is actually just relating the reference angle. And again, you need to understand when we're dealing with the tangent inverse, that's only going to give you, the tangent inverse is only going to give you an angle in the first and the fourth quadrant. So it's being applied, it's going to have that domain restriction on it from tangent. So therefore, our angle is only going to be in the first and second quadrant. So therefore, we just have to use a little bit of math and understanding to recognize we need to add 180 to give us an angle of 4, 240. So I just have a couple more points that I gave my students. And what I'm going to do is I'm just going to do, again, a rough sketch just so I can visualize this to make sure things are working. So I'll have a negative 9, positive 3, because I just want to make sure I have this in the right quadrant. Okay, so at least I know it's in the second quadrant. And therefore, when I find my angle, it's going to be a little bit easier for me to make sure that I'm finding the correct angle. So now what I'm going to do is just do negative 9 quantity squared plus 3 square root of 3 quantity squared equals r squared. So this is 81 plus, let's see, it's going to be 9 times 3. It's going to be 27 equals r squared. Now in this case, when I add them up, I'm getting 108. So again, 3 times 3 is 9. Square root of 3 times square root of 3 is 3. 3 times 9 is 27. So r squared equals 108. And you can just say r equals the square root of 108. Okay, and we'll just leave that. That's fine. There's nothing wrong with that. So our r is going to be the square root of 108. You could simplify that, but we typically just kind of focus on or look into simplifying it. That for this chapter, we're not going to be simplifying our radicals. We'll just leave them as they are. The next thing then, I want to be able to figure out the tangent. So I'm going to do the tangent of theta is going to be 3 square root of 3 over negative 9, which is going to leave me with a negative square root of 3 over 3. Okay, So hopefully you recognize that is going to be for 30 degrees. So when I do tangent inverse of negative square root of 3 over 3, that is going to give me in my calculator a negative 30 degrees. But again, that doesn't make any sense, right? Negative 30 degrees is over here. My point is over here, right? So we need to understand that negative 30 degrees, what that's doing is that's giving you the reference angle, right? That's giving you this angle right here. But again, we're not trying to find that angle. We're trying to find the angle in standard form from here to here. So hopefully you can recognize that this is just going to be this angle. My calculator, because tangent inverse gives me negative 30 degrees, that's going to represent the reference angle. So therefore, it's going to be equal 150 degrees. All right, again, same kind of thing. This is one's a little bit easier to go ahead and plot, but we're going to have a positive 5, negative 5. It's going to be down here. So again, if I wanted to find the distance, how far is this away? You can think of that's 5, that's negative 5. So just going to do 5 squared. So r squared equals 5 squared plus negative 5 quantity squared. R squared is going to be going to equal to 50. And again, r then is going to be the square root of 50, but we'll just leave that in the radical form there of square root of 50. We'll just leave it as that. So therefore, r is going to be square root of 50. Now we need to figure out the angle. So we'll have tangent of theta is going to equal negative 5 over 5. So theta equals negative 5 over 5 is just negative 1. So that'd be a tangent inverse of negative 1. And hopefully you recognize that negative 1, that's going to be a negative 45 degrees. Or if you were to plug in your calculator, that would give you negative 45 degrees. Now in this case, we can use the angle to be negative 45 degrees. Like that's perfectly fine. Or we could use the positive version. Like it doesn't really matter. That's a multiple representation here. So again, my r is going to be 50. And this would be negative 45 degrees. Again, or you could do square root of 50, comma, let's see, that'd be 315 degrees, right? So it doesn't really matter if you want to use the negative or the positive. Obviously, it would kind of depend on the question from you. And then again, just remember, you could also do different representations for all of these, which I kind of forgot to do over here. That was one thing I mentioned with my students. You could do 240. You could also do a couple other variations here. You could do the negative version, right? Which would be, let's see, 60 away from 180. So you could also do 4 comma negative 120. You could do, what about the negative? If you made this a negative 4, so this is going to be our answer. But if you did a negative 4, that's a reflection about the origin. So you could do 60 degrees. Or you could do a negative 4, negative 300 degrees. So you can see how these are both kind of variations to produce or to give us this exact same point. But obviously, if I just want to convert this to polar form, that's going to be my answer. But again, if we were looking for maybe a different types of questions as far as looking for different variations, you can see how we can arrive at that. Okay, so now let's go ahead and think about working on equations. So how are we going to convert from polar to rectangular equations? So polar equations are basically equations that are in terms of r and theta, whereas rectangular equations are going to be angles that are in terms of x's and y's. So our goal in this case is going to to eliminate our r and our theta. So two things we know. We know that r squared is equal to x squared plus y squared. So if I have an r squared, or if I create an r squared, I can replace it with x squared plus y squared. And then we also know if I have r times cosine of theta, we can replace that with x. And if I have r times sine of theta, we can replace that with a y. All right. So in this first example, you can see that I didn't have either of those, right? So I can't replace r with anything. It needs to be either multiplied by cosine and sine or be r squared. So the easiest way to create an r squared would just be to square both sides, right? And this is something we don't use as much because, when solving equations, that produces an extraneous solution, and we wanted to avoid that. But in this case, it's going to be perfectly fine for us to do it. We're just, converting from one equation to the next. So I go ahead and square both sides. And then that gives me r squared equals 9. And then I convert r squared to x squared plus y squared equals 9. And then I can describe the graph to be a circle with a center at 0, 0 and a radius of 3. And this is, again, going back to our representation that we talked about last class period. The other thing is it kind of makes sense. Like if you think of r is equal to 3, that's the only thing you know about the equation, right? The distance away from the origin is 3. Well, that's just going to create a perfect circle, right? All right, the next one is theta is equal to 60 degrees. And again, the only way I can use theta if it's like r times cosine of theta or r times sine of theta, or, and I forgot to mention this, or if it's tangent of theta equals y over x. So multiplying by r, taking the cosine of both sides and multiplying by r doesn't seem like it's really going to simplify this much. However, taking the tangent of both sides is definitely something that works, and I can easily do. So when I take the tangent of both sides, I now have tangent of theta equals tangent of 60 degrees. Tangent of theta is y over x. Tangent of 60 degrees is the square root of 3. Now, to solve for y, I just multiply by x on both sides, and you can see that I get a line. That's an equation, y equals mx, right? Plus b, where b is 0. But you can see the slope is square root of 3, which is kind of weird, but it works, right? That's going to produce a line. And again, like it kind of makes sense again. If we go back to that polar equation, if you have something that's always 60 degrees, right? Even when you have a negative direction, it's still going to be a 60-degree angle. You can see that's producing a line. All right, and then the last example I covered with my students was when you have r equals 4 times sine of theta. And again, in this case, we need to we have a sine, so basically we want that to be multiplied by r, and that's going to give us y. Well, we just can't multiply one side and not the other side. And also, we recognize there's an r on the left side anyways. So when I multiply by r on both sides, I get an r squared equals 4r sine of theta. I can convert the r squared to x squared plus y squared equals 4y. Now, technically, that's done. However, in preparation for next chapter, what I did is I helped students go ahead and rewrite this into what we call our standard form, which is basically going to be representing, well, this is not fully in standard form, but at least representing the circle or representing our equation into our being able to identify the center, and by creating the binomial squared. And the way that we're going to do that is by completing the square. So what we want to do is get all the x's and the y's to the same side. You can see I can group the y squared minus 4y together. And then what I want to do is create a perfect square trinomial. And again, I'm not going to get in depth with the completing the square because we're going to spend more time more in depth on that in next chapter. But again, if you recall, that's the b divided by 2 squared equals 4. You can plug that value in. Then that produces a perfect square trinomial, which can be factored down to a binomial squared. And then you have it in this form where it's a little bit easier to identify the circle with a center of 0, 2 and a radius of 2. And again, this is a little bit extra explanation that I went through with my students just to make sure they felt comfortable with the material. And then we went ahead and practiced doing some other equations. So in this next one, I'm not used to secant. Like, what should I do here? Well, again, like if I have an r, I want the r to be multiplied by cosine of theta, right? It's either I square both sides, multiply by r on both sides, or multiply by cosine of theta. So when I multiply by r cosine of theta, I get r cosine of theta equals 2. Because secant of theta times cosine of theta, those are reciprocal functions of each other, so it's equal to 1. And again, r cosine of theta is equal to x. So that equals 2. And voila, we're done. Next example is just like I did in the last one. I'm going to multiply everything by r. So that gives me r squared equals a negative 4r cosine of theta. Again, now this is going to represent x. So I can say x squared plus y squared equals a negative 4x. Now I'm going to do the same process over here. I'm going to have, let's see, that's going to be becoming x squared plus 4x plus y squared equals 0. And then again, basically I'm saying if I wanted to create this as a perfect square trinomial, like x squared plus 4x plus what number here is going to make this a perfect square trinomial? Meaning what number where the exact same number add to give me 4x, what would they multiply by? Well, what is the one number that's exactly the same that adds to be 4? That's 2, right? 2 plus 2 is 4. Well, then 2 times 2 is 4. But again, you just can't randomly, did I forget to do that? No, okay. You just can't randomly add a 4 to the left side without adding it to the other side. So that's why I'm going to add a 4 here on the other side. Then this can now be factored down into x plus 2 quantity squared plus y squared equals 4. And now you can see that that is an equation. So again, that's perfectly fine. But from here, a little bit extra, you can see that the center, or sorry, that it is a circle, but with the center at -2, 0, and a radius equal to 2. So very, very similar to our last example. All right, so for the next one, we're going to want to do the same thing. Like if I have a cosine of theta, sine of theta, I want those to be multiplied by r. So I'm just going to multiply everything times r. So I'm multiplying everything times r. I get an r squared equals 6r cosine of theta minus 2r sine of theta. Now that produces a x squared plus y squared equals a 6x minus 2y. And again, like technically we're done right there, right? I have now written the equation from r's and thetas to x's and y's. So that is the rectangular equation. However, just in case your problem is not in this form, like for instance on a multiple choice, we want to make sure that we can write this in our standard form, or at least identifying the center and the radius. So what I'm going to do is I'm going to get all the x's and y's to the same side. And actually, I'm just going to rewrite this for the sake of space. Plus y squared plus 2y is equal to 0. Now you can see I'm going to group my x's and I'm going to group my y's. And basically what I want to do is say, all right, what number should I add inside these parentheses to create a perfect square trinomial? Again, what number is exactly the same that adds to give me -6? And again, that's going to be a -3. -3 plus -3 is -6. -3 times -3 is going to be a positive 9. And if you forget, you can always do opposite of b divide, I'm sorry. Well, it doesn't matter. Opposite of b. I was thinking the line of symmetry. b divided by 2 squared, right? That's the same thing. If you take -6 divided by 2, that's -3. -3 squared is going to give you 9. So this always works in that case. But again, our goal here is to create this perfect square trinomial. You can see here, if I add a 4, that produces that, a perfect square trinomial. Or just do the b divided by 2. 2 divided by 2 is 1. I'm sorry, 1 squared is 1. So you can see I did do that great in my head. So that's going to be 1 equals 0. But again, I have now produced two perfect square trinomials, which now can be factored down into x minus 3 squared plus y plus 1 quantity squared equals 0. Therefore, again, it is a circle with a radius. Oh, I'm sorry. It doesn't make any sense, guys, for it to equal 0. That means the radius would equal 0, right? I'm kind of working myself way too fast, so I'm going to slow down for a second. Remember, if you add a 9 to the left side, you can't just randomly add a 9 in an equation to the left side without adding it to the right side. Otherwise, the equation's not balanced, right? Back to like 101 of equations. Same thing over here. You can't just add a 1 to the left side without adding a 1 to the right side. So therefore, that's going to equal 10. So this is important because now r, my radius, is the square root of 10. And we can say that the center is going to be the opposite of my h and my k, which is going to be a 3, -1. All right? Okay. For the next example, kind of looks a little interesting here. Well, I figure if I'm going to want to convert this, I'm going to want to get this off the denominator. So what I'm going to do is I'm going to multiply both sides by 2 cosine of theta minus 3 sine of theta. Okay, so I'm just going to multiply the whole equation there. So then what I'll have is r times 2 cosine of theta minus 3 sine of theta on the left-hand side. And on the right-hand side, those will now divide out, right? So therefore, I'll just be left with 6. Well, I can now distribute this r to give me 2r cosine of theta minus 3r sine of theta equals 6. And again, now you can see I have r cosine of theta, r sine of theta. So this could be 2x minus 3y equals 6. Okay, so now you can see that's in rectangular form. Obviously, guys, again, you could write this as slope-intercept form if you needed to. Let's see, that could be -3y equals -2x plus 6, and then divide by -3. So y equals a positive 2/3 x minus 2. right? So you could subtract the 2x, divide by -3, and you could also do a slope-intercept form as well. Okay, so to convert from rectangular to polar, I think it's actually a little bit easier because the problem with these is you didn't, every single, except for these two problems, everything else was kind of different, right? Here we had to multiply by cosine. Here we had, these two we had to multiply by r. Here we had to multiply by the denominator on both sides. Like it's different for each one of these. But for rectangular, it's usually kind of like the same process. You're just going to want to replace your x and y's with r cosine of theta, r sine of theta. So it's kind of like straightforward. So in this first example, if I just replace my x with r cosine of theta and my y with r sine of theta, like I'm done. Like basically that is now a polar equation. It's in terms of r's and thetas, right? Because again, our whole goal is to replace x and y's with r's and thetas. However, typically when we're solving for an equation in polar form, we want to have it solve for r. So what I'm going to do is factor out an r because I can't combine them because they're not like terms, right? So I'm going to have to factor out an r, then divide by 3 cosine of theta plus 2 sine of theta to give r equals 4 divided by 3 cosine of theta plus 2 sine of theta. In the next example, again, kind of the same idea. I don't want to replace, well, first of all, before I get to the same idea, I don't want to replace x with r cosine of theta and y with r sine of theta right here, because then I'm still going to have to square them, right? And it's going to kind of, I mean, I guess you could just replace them and then you're done. But if you have an equation that's solved for r, it's going to be a lot more difficult to square things and then try to simplify. So the way that I looked at this, because then you have a sine squared plus a cosine squared, and I think it'd kind of get a little confusing from there. But actually it's still, yeah, it's still, maybe I'd have to, I don't know. I didn't work it out. But either way, the way I looked at it is it's much easier to expand these with variables. And when I expand these with the variables, then I just group my x squared and my y squared together and my 6x and my 6y together. So therefore I knew x squared plus y squared, that gives me r squared. I can rewrite this in terms of, I don't know why I'm using x. Let's use thetas. I like converted x's to thetas, but I don't want you to confuse, I want you to confuse all these thetas with the actual variable x because they're not. So then I converted the 6r cosine of theta to just cosine of theta, sine of theta. Oh, r times cosine of theta, yeah. Sorry, I converted the x to r cosine of theta, the y to r sine of theta. Okay, and then we come into another situation. This is where it's similar to this one. We have multiple r's. If we need to solve for r and we have multiple of them, typically our goal is going to either combine them or to look into factoring out a common element or factor out the r. Well, in this case, we can't combine them, so I'm going to factor out the r. Now, when I factor out the r, I'm still left with, I have a factored form of r times r plus 6 cosine of theta plus 6 sine of theta. So again, since I have the product equal to 0, I can apply the 0 product property. That's good. So therefore, I'm going to set both products equal to 0. So r is equal to 0, and then r plus 6 cosine of theta plus 6 sine of theta is equal to 0. But again, r equals 0, that doesn't make any sense, right? That's like the distance away from the origin. It's like a dot. So it's not even actually a graph at all. So the equation is, we're just not going to represent that. That's not going to represent this equation. So therefore, then I just have this equation. I'll set this equal to 0, and that is the equation I'm going to use because that's not going to represent that, right? That's like a dot at the origin. All right, and then I just gave my students 4 more problems to do, and you can kind of see, we'll just, kind of work through them in this case. So again, from here, I can just replace y with r sine of theta. -2, when I divide by sine of theta on both sides. That's the same thing as like rewriting this as cosecant. So you'll most commonly see this as cosecant of -2 cosecant of theta. For b, again, first thing we want to do is really just expand this out. So, again, remember x minus 2 quantity squared is x minus 2 times x minus 2. It does not equal x squared minus 2 squared. Okay, that's one of the more common things that I didn't mention in my previous example, but it's one of the more common mistakes students will make. So you actually have to multiply this out. So this is going to mean x squared minus 4x plus 4, always happens like that, plus y squared equals 4. Now again, here we have an x squared plus a y squared. So therefore that's going to equal r squared minus 4 times r cosine of theta equals 0. Right? So you can see what I did is I grouped, actually let's just show my work here. Let's just group everything. So I have x squared plus y squared minus 4x plus 4 equals 4. Okay, so we can subtract the 4 on both sides. This gives us r squared. And then we have 4 r cosine of theta. And again, we can't combine them, but we can factor out our r. And that'd be r minus 4 cosine of theta equals 0. And therefore that is going to not produce that equation. So therefore we can just focus on r equals 4 cosine of theta. For next example, we have an x and a y. So I'm just going to replace the y with r sine of theta and the x with a r cosine of theta. Okay. And now to solve for r, I basically want to get the x and y to the same side. So I will subtract a 2r cosine of theta. Okay, and again, we can't combine them, but I can factor out an r in this case. That would give me a sine of theta minus 2 cosine of theta equals 4. So r is going to equal a 4 all over sine of theta minus 2 cosine of theta. All right, and then the last one is going to be just like the one I did up here. So I will kind of skip over a little bit of steps, or at least just not show everything. But again, hopefully we can expand this out. So when I expand this out, that's going to give me an x squared minus 4x plus 4 plus a y squared plus 2y plus 1 equals 5. I'll group these together. So x squared plus y squared minus 4x plus 2y plus 5 equals 0. Then I can rewrite this as an r squared minus 4 cosine of x plus 2 sine, why am I doing x? I don't want to confuse you. Let's use theta plus 2 sine of theta. That's equal to 5, forgetting some things, equals 0, right? You can just subtract the 5s. And then I forgot my r's. Dang it. Going too fast. So let's subtract these 5s here. Okay, so 4x becomes r cosine of theta. Y becomes r sine of theta. Very good. Now we factor out the r, and again, we're going to be left with a r minus 4 cosine of theta plus a 2 sine of theta equal to 0. Again, this r is going to go to 0 or a set equals 0, and it's fine. Therefore, we have r equals 4 cosine of theta. So if you set this equal to 0 minus a 2 sine of theta equal to 0. Oh, I'm sorry. There you go. Slow down. So there you go, ladies and gentlemen. That is our lesson on polar equations. Hopefully that it was helpful for you. What we covered is, again, converting between rectangular and polar points, finding different representations, as well as converting between rectangular and polar equations. Hopefully you understood some of that. And if not, please feel free to put your comments down below, and either myself or hopefully somebody will be able to answer your questions in the comments below. And otherwise, I look forward to seeing you on the next video. Cheers.